Great to see you all here. I am very excited that this week we have Andrea Lopez Lang here as our presenter. Andrea is, as many of you already know, was a faculty member, is still a faculty member at University of Albany, but that will be wrapping up, and she is soon to start as a faculty member at University of Wisconsin-Madison. So we'll check in with her in 5 years and see what other university she decides to become a professor at, but I'm not gonna limit you in any way, so this is great. Andrea works on synoptic to large-scale atmospheric dynamics, and then on weather, and then the impact of that on weather from, relative shorter to medium range maybe to seasonal timescales. So it's an area we have a lot of interest in here at NCAR, and predictability, and also how does tropospheric, stratospheric interplay play a role in that. That's something I also myself am very interested in. I hope all of you will learn a lot today. I'm sure you will. So beyond research, Andrea is committed to bridging the gap between student academic experiences and the breadth of career opportunities in atmospheric science. And as an example of that is the Mind the Gap program, did you found that then, which some of you may have heard of. And Andrea was just telling me there's now on the COMET page, part of the COMET program, new modules up that can be played in classrooms that say if you're talking about drought, it's actually interviewing, decision makers in the drought space and who's using that data. I think that's just a wonderful thing. A lot of academic programs haven't always had that part. And it's a terrific thing for a student to get exposure to that. She was part of the inaugural class of the American Meteorological Society's Early Career Leadership Academy and recently completed a role on the AMS Council. I'll just say thank you for being on the AMS Council. And she's the chair of the AMS Board on Enterprise Economic Development. Also, thank you for that. And she's currently a member of the National Academy's Board of Atmospheric Science and Climate. So it's just a real pleasure to have you here, Andrea, and I will let you take it away.
Thanks. I think this mic is on. Hopefully, this is my last move and James won't pull me anywhere else to other universities, so that's the plan anyway. So thanks, Gretchen. I'm really excited to be here. This is my first visit to NCAR as a visitor instead of here for a workshop or the other great things that happen at NCAR. So I'm excited to present a little bit of research that's happening in my group. Some of you were able to attend the happy hour seminar yesterday. So some of the things I might refer to might hint back at that, but I'll try to make sure that I cover everything. So what I want to do today is talk about winter extremes. So my work is really focused on the extratropical winter extremes. And I just want to say that this doesn't happen just with me, it happens with my research group. So these are some of my grad students, current and former, that have contributed to the work that we'll see here today. And this work is funded by both ONR, thinking about extended range predictability in the high latitudes in the polar regions, but also by NOAA, thinking about the importance of lower stratospheric processes in the dynamics of our weather systems. So what I want to do is I want to highlight what we're thinking about when we think about winter extremes. So usually we think cold weather, snowstorms, cold air outbreaks, that sort of thing. But if you look at the US billion-dollar disasters list and you focus only on the winter season, what you're looking at here is the distribution of the different billion-dollar disasters through the winter season. And so when I say winter season, I'm DJFM, I'm also including March. And this is current through this year. And every type of disaster, except for tropical cyclones, has happened during the winter season. And if you look at this, of course, we have towards the end of the plot, winter storms and freezes. Of course, the majority of those happen in the winter season. But if you look at the numbers, that's how many of the total of the billion-dollar disasters have happened in DJFM. And you'll see the maximum number is severe storms. So even though we think of severe storms as a summertime event, still out of all the billion-dollar disasters that have happened in DJFM, severe storm related events are the maximum. So I just want to give you that perspective as we're thinking about winter extremes. And as I say that, I'm going to focus on cold air outbreaks for the first part of the talk, but then we'll touch back to severe storms. So I also want to think about, okay, so billion-dollar disasters, extreme events, why are we interested in predicting these at extended timescales? And if we think about this, we think about our continuum of different types of forecasts and outlooks, ranging from, extreme tornado forecasts happening in the next minutes to hours, all the way to climate prediction, where we're looking at outlooks. There's decisions that are made in association with these forecasts and outlooks. So there's this space where we can think about how each type of our forecasts sort of fit into the decision-making spectrum. And so, of course, we have our weather forecasts that we know and love, and then we have our climate outlooks and climate forecasts, sort of thinking about years to decades. And then we have the subseasonal to seasonal forecast timescale that really is thinking about the timescales of a few weeks to a couple months. And there are a lot of extreme phenomena that happen and can be predicted, or at least the probability or likelihood of these events, we can see some indication that there's an increased probability or decreased probability of these events at these timescales. So these are some of the things that I'm thinking about, are how we can really identify and enhance our forecasts of opportunity of these events at these subseasonal to seasonal timescales. And so there's been a lot of work looking at this, and I wanted to make sure that I include this caveat that this is a summary of a lot of the papers that were in the special collection on subseasonal to seasonal prediction. So in this collection, there were things looking at model setup. We were looking at different processes, physical processes. And this figure is extremely complex on purpose because the idea is that the subseasonal to seasonal timescale isn't easy. There's a lot of players, there's a lot of things going on. And so really, I'll be talking about the role of stratospheric variability in subseasonal predictability and the subseasonal timescale. But I want to make sure I include this caveat that it's not the only player. It contributes to variability at these timescales. So from that perspective, we can think about anomalous stratospheric conditions as a way to modulate the tropospheric flow at subseasonal timescales that can extend the predictability or increase the likelihood or decrease the likelihood of extreme events at these timescales. So it's one of many contributors, but that's what we're going to focus on here. So what I want to do is I want to think about the stratospheric polar vortex in particular, so high-latitude stratospheric variability. And when you think about that, you probably think about something like this, where we know that the polar vortex attacks the US and we get cold air outbreaks and a lot of great news headlines. I think one of my favorite ones is this top one, where it's the Brits are hit with snow and 3,000 miles circle of winds due to the frozen donut at the top of the world. So this is really what our stratospheric polar vortex, what is this? And we can, it kind of resembles a donut, so I'm okay with this analogy. But for those of you that don't really think about the polar vortex a lot, I just want to give you a little bit of background. So why do we have a polar vortex? It's not there all year round. It's really a wintertime phenomena. So in the polar winter night, when our high latitude regions are pointed away from the sun, we get decreased solar radiation and we get a polar night. And so this is what really produces the polar vortex. So we have a strong temperature gradient associated with a large long wave radiative cooling, especially in the stratosphere. Ozone is a long wave radiative cooling. So the stratosphere has a lot of that. When there's no heating associated with solar radiation, there's a lot of cooling. And so we get a really strong temperature gradient. That temperature gradient via thermal wind is associated with a really strong jet. And so it really is together the cold polar cap and the winds that are the polar vortex. So it's both of these together. When we're thinking about the polar vortex, there's both the thermal part and the momentum part. So this is climatologically what's happening in the wintertime, but there's a lot of variability associated with the polar vortex. And so when we have this variability, we can think about strong vortex conditions, and during these strong vortex conditions, we have a really cold polar cap, and that produces a really strong vortex. And if we were to take a cross-section from the polar regions to the equator, and that's what you're seeing in that far side, there's a vertical structure to the polar vortex. So sometimes when we have a really strong polar vortex, it can be connected with what we see in the troposphere. So we have our tropospheric or tropopause jet, and then we have our stratospheric jet. Sometimes they're coupled. And when we have strong polar vortex conditions, usually the PV gradient, the waveguide, is really strong, and we have reduced wave interactions between that stratospheric jet and the tropopause jet. This really keeps the cold air in the polar regions, keeps the warm air where it's supposed to be, and it can shift the storm tracks in the northern hemisphere poleward. When we have weak vortex conditions, we have increased wave activity along that PV gradient that gives us our jet. This moves the storm track further equatorward in the northern hemisphere. We have warmer stratospheric conditions, weaker winds in the stratosphere, and so really this is the background where everything is set up. So typically from this sort of zonal mean, really climatological perspective, strong vortex conditions, cold air stays at the pole. Weak vortex conditions, we don't have that constraint where cold air can be, so we can have warm or cold extremes somewhere in the northern hemisphere. And so our question is, how frequently does that cold air come towards the US during these weak vortex conditions? So climatologically, again, during these weak vortex events, there's patterns of variability that are sort of expected. And some of these patterns, this is a composite of 37 different weak vortex events. And it's the 60 days after these 37 events. So there's a lot of days averaged in here. And from these averages, we see that storm track shifted, especially in the North Atlantic region. So we tend to see a shift in the storm track a little bit further south. And that produces a lot of impacts, especially for Europe. We also see that there's temperature variability associated with weak vortex conditions. The highest or the largest impacts, again, are Siberia and Eurasia. And then we also see, because the storm track has shifted, we also see variability in the precipitation distribution. So these are some of the things that we know about stratospheric variability, so trying to understand when and how it's going to impact us is the question. And so there's known ways for these processes to evolve, and really it evolves vertically in time and in space. So the way we get stratospheric variability is we have a source of anomalous wave activity in the troposphere, and I think actually I have a cursor. So we have wave amplification in the troposphere. That's one of the requirements. The sources for stratospheric variability are in the troposphere. Then we have upward propagation of these waves. So usually we think of downstream wave propagation, but when we include the stratosphere, it's really 3D. And so we can actually identify when we have upward propagating waves or a reduction in upward propagating waves. But either way, in increase or decrease, we can have variability in the stratosphere that can produce strong or weak vortex events. And then once that happens, we have this downward propagation of that strong vortex signal back into the troposphere. So this is the pathway for how the stratosphere can impact the troposphere. And it turns out that the predictability of the upward component of this process is really only on synoptic timescales. So this is really a weather. We're thinking about wave amplification, how waves are propagating. That really is weather timescales. But it's this downward side is where we get our subseasonal predictive skill and where we can think about forecasts of opportunity. And I just want to emphasize this first synoptic timescale part. We've done an analysis through a group of us coordinated through Spark, where we looked at all these different types of stratospheric variability. And no matter what type of stratospheric variability we thought about, really all the ensemble models that we were looking at from various operational centers that contributed to the subseasonal to seasonal prediction project really only had predictability at these weather timescales. So I just want to emphasize that. We've looked at it, we've quantified it, and unfortunately, that's how it is. Okay, so now let's get to the impact side. So let's focus. I showed you that the highest impacts are over Eurasia and Siberia, but the question is, what about here in the US? Can we use information about the polar vortex to say something about outcomes in the US? So I want to focus on colder outbreaks because that's where the big headlines come from. So let's think about colder outbreaks first. And I just also want to mention that attribution for events being related to stratospheric polar vortex variability are kind of hard in real time. We're getting better and we can start to identify processes, but there's still a lot of uncertainty in models and all of that. So I just wanted to put that there too. So let's think about one of the biggest colder outbreaks that have happened recently. And we can think about the February 2021 big colder outbreak. This colder outbreak was also associated with the only time when the entire state of Texas was under a winter storm warning, including South Texas, which reaches 26 degrees latitude. So that's pretty impressive. And what you're looking at here is these little thumbnails are daily averaged 1,000 hectopascal temperature anomalies. And it isn't so you can look at the details of where the temperature is, but it really is to show you that this colder outbreak evolved over a period of a week, 10 days or longer. So you can start to see the cold air coming from Canada. You can see that Canadian cold air being advected southward. The Rockies are involved, cold air damming. And we can see that even just eyeballing this February 15th appears to be the coldest day, and it was the coldest day through the month of February. And this was the biggest cold air outbreak, billion-dollar disaster in the NOAA dataset. It was over $26.5 billion in insured losses, so that doesn't include non-insured losses. Record-breaking energy demands, and we know that from the catastrophic energy failures that happened. And this was a level 3 energy emergency alert. I wasn't aware of these until I started looking at this case, but this rarely happens. And essentially, these are prescribed outages from the different power pools because they are expecting energy demand to exceed what they're able to produce. And if you look at where the cold air is happening, where we have our largest temperature anomalies, it happens to align with these two power pools. And as we've learned, and probably everybody's heard since then, in Texas, ERCOT isn't really coordinating with the adjacent power pools or energy utilities. So they're really isolated. So this event really impacted them a lot. Okay, so this is the event. So how well did we predict it from a subseasonal timescale? And so what I want to show you is this happened in February, mid-February. So let's go back to subseasonal timescales and look at forecasts initialized in January from subseasonal forecast models. And that's what you're looking at in this plot. So the black line is showing you the average temperature anomaly in this box, so a big chunk of the center part of the US. So that's the black line, and you see some variability. And then we see our big cold air outbreak with the coldest on January 15th. So again, that's that day that looks like the coldest day. And then these different color lines are forecasts from ECMWF, JMA, and our ECC, that's Canada. So these are their subseasonal models. And as they get to be the more muddled version of their colors, it's lead times that are closer to the actual event itself. But essentially what you see from here is that none of these models, S2S models, were able to resolve the forecasts of this extreme cold air in the central US. So we have, we missed this cold air outbreak. But we know from previous analyses, for example, John Albers and co-authors did an analysis of this event and looked at the predictability of this event, and they showed that there were different modes of variability at S2S timescales that increased the likelihood of its occurrence from sort of an idealized sense. And they were able to show that the La Nina conditions at the time, the MJO, and stratospheric variability all contributed. So what we were interested in is that was an idealized thinking about EOF space and how we can use that to make predictions. But using these operational models, were we able to actually see the contribution from the stratosphere? And did it impact this whole area or not? And so what we did was, we looked at different lead times. And essentially by week 2, we were able to resolve this. At week 3, 4, and 5, lead times not so much. But we split it up into a northern part of the cold air outbreak and a southern part of the cold air outbreak. And what we started to see was that the southern part of the cold air outbreak is where we really had very little predictability. But as we look at week 3, we notice that there is a big difference between the purple models and the yellow models. And that's the difference between the high top and low top models. And what I mean by that is high top models include a well-resolved stratosphere. Low top models don't. So what we were seeing was that models that included the well-resolved stratosphere had a little bit more predictability, but only in the northern section of this cold air outbreak. So why did the high top models outperform the low top models at this 3-week lead time? So then we dig into what was going on in the dynamics. So I want to go back to some literature, and this is a review article, and it's a good one if you're interested in how stratospheric variability impacts the troposphere. And these are different types of stratospheric variability and how they impact the troposphere. But in North America, for cold air outbreaks, there was work by Matthias and Kretschmer in 2020 that showed that there's stratospheric Rossby wave reflection events that can impact cold air outbreaks. And so maybe you've heard of that, but probably not, because this is something that really has not been looked at in a lot of detail in terms of how it impacts North American weather. So this is what this looks like. Here is an evolution of the 850 hectopascal temperatures. Those are the color fills. And then what you're looking at is the 50 hectopascal geopotential heights from the 1st to the 10th of February of 2021. And then what you're looking at in this plot, this cross section, goes from the prime meridian through the date line in the center, all the way to the prime meridian again. And it's a cross section going from 1,000 hectopascals to 1 hectopascal. And you're looking at where the troughs and ridges are in colors, and then we see the wave activity flux. So essentially this is telling you something roughly along the lines of the group velocity of Rossby waves. So what we have is we have Rossby wave activity being fluxed upward in the eastern hemisphere, in the lower stratosphere. Then it's being reflected back downward, where it's converging right at the tropopause level. And this is what we're seeing. So we have Rossby wave source over Siberia, and then we have a Rossby wave sink, where the waves are amplifying, the local trough is amplifying over North America. And really, this is the process where we're setting up the background flow to get a really big trough over North America that can lead to that northerly flow that brings us the cold air responsible for the cold air outbreak. So, this was happening in this case, but this isn't the only time wave reflection has been associated with cold air outbreaks. This Matthias and Kretschmer paper was a composite of 41 different wave reflection events. And they were able to show, this is a particular case study, but many of these events were associated with at least colder conditions in North America. So our question is, okay, well really, we heard that things like sudden stratospheric warmings and weak vortex events can produce high amplitude flow. There's strong vortex events. Now we have these wave reflection events to consider too. So let's really dig in and say, there's all these types of stratospheric variability. What's going on and how are they related to things in North America? So here we are, we have these stratospheric reflective events, and we can identify them, we can think about them. And what we're interested in is identifying these wave reflection events. And so this is what we're looking at here, these wave activity flux vectors. We can identify these wave reflection events in 2 ways. And so a wave reflection event doesn't necessarily need a strong vortex or a weak vortex situation, they can happen independently. So we have two metrics that we're going to identify conditions for these wave reflection events. One is particularly looking at the eddy heat flux, eddy meridional heat flux in two boxes. One of the boxes is centered over eastern Siberia. So this is the upward component where we're looking for upward wave activity flux. And that is directly proportional to the meridional eddy heat flux. So that's why we're looking at it here. And then we're looking for a downward component over North America. So this is going to be our VT, meridional eddy heat flux, reflection index. So we'll call it VTRI. And then there's another metric that was proposed in 2003 that's really looking for the conditions that favor wave reflection, and that's really the easterly shear in the upper stratosphere. So we're looking at easterly shear from 10 to 2 hectopascals. So this is way up there. 10 hectopascals is roughly 30 kilometers, so we're talking about way up there. And these wave reflection events are reflecting planetary scale waves. So we're talking planetary scale wave 1 and wave 2. So our question is, how many US cold air outbreaks are actually associated with these, or weak vortex events or strong vortex events? And if we can identify that, can we actually identify the indicators that tell us in advance that we're more likely or less likely to have a cold air outbreak in association with one of these events? So to do this work, we first had to identify cold air outbreaks in our data set. And what we're thinking about is these 57 cold air outbreaks that we've identified in the ERA5 data. And we've really identified the most intense cold air outbreaks where they need to have an area where the minus 1.5 sigma cold air exceeded some threshold that roughly is about a quarter of the US. And they had to last at least 72 hours, so we identified 57 events, and this is just an example, a cold air outbreak from 1985. And so these events are all extreme events, and this is just an example news story from this particular 1985 cold air outbreak. There were over 100 deaths associated with this cold air outbreak. Florida lost about 89% of its citrus crop from that cold air outbreak. The thruway in New York was closed for several hours. So this was a high impact event. And so these cold air outbreaks, these 57 are all of these types of extreme events. So a composite of these events, they look like what you would expect: huge trough over the US. The 500 hectopascal geopotential height is in the pink. The 10 hectopascal, so the polar vortex, is in black, and then the color fill is the 850 temperature anomaly. And so we expect cold air over the US, that's what we're identifying, but you can also see the big ridge over Alaska that we typically expect with these cold air outbreak events. And so then now that we have these events, we can also look at, from 1959 to present, climate change signal is there. The area of cold air outbreaks is decreasing with time. The duration of cold air outbreaks is decreasing with time. And you can really see that January, this is the number of cold air outbreaks by month, going from the first 30 years to the next 30 years. And it's really January seeing the biggest drop in cold air outbreaks. Okay, so we identified cold air outbreaks. We got all this data, area, duration, intensity of the coldest cold air. And so now we need to identify our stratospheric events. So we have our differential, our DURI, differential U. So this is the easterly shear to identify wave reflection. And so this is how we identified them. We have these eddy heat flux wave reflection events, and we've identified them here. And we have some metrics, and so we're documenting how we're identifying these. So we've put together this data set, and now we have these 64 identified easterly shear conditions that are favorable for wave reflection. And then we've also identified 71 events where we have this huge difference in the upward heat flux, or the upward wave activity flux over Siberia and downward over Canada. So we now have this, and we can compare that to our cold air outbreaks. And this 1985 cold air outbreak event was an easterly shear reflective index event, but not one of these eddy heat flux reflective events. So I just want to emphasize that these two metrics aren't necessarily identifying the same dynamics. So they're not the same events that we're looking at in this particular analysis. All right, so then we also, to be consistent, looked at strong and weak vortex events. We found 53 strong vortex events since 1959 and 42 weak vortex events. Our weak vortex events, I'm calling them weak vortex events and not sudden stratospheric warming because we do include a few events that aren't necessarily sudden stratospheric warming. They're final warming events, but that gets into some minutia and details. Okay, so now we have all these events and we can look at how these stratospheric events change by decade and when the months that they're likely to occur. So we have all this data and now we can do this really in-depth analysis to try and understand the relationship of stratospheric variability to cold air outbreaks. And so what I want to emphasize here is that there's a known lull in sudden stratospheric warming and weak vortex events in the 1990s. So there were only 2 in the 1990s, but there was a maximum for the other type of events. So the stratosphere was still active, and a lot of the weak vortex event lull was associated with the reduction in ozone during the 1990s. So this is a whole nother question. But I just wanted to mention that there's no major signal in the trend for stratospheric variability in the ERA5 data. And so in terms of months, the active months are, of course, December, January, and February for all of these events. And so that's pretty consistent with prior literature. Okay, so let's get, how are these events related to cold air outbreaks? So what we're looking at here is the occurrence of cold air outbreak after different types of stratospheric variability. And so this is what we expect based on a bootstrap resampling of 7 days, in the 7-day window after a weak vortex event in red, strong in blue, reflective index from the shear metric in green, and then a reflective index from the heat flux metric in purple. So we have our 4 different types of stratospheric variability, and we have different windows. So we're going from in the 1 week after a stratospheric vortex, 2 weeks, 3 weeks, all the way to 5 weeks. And so this is the expected distribution. And so now we can add the observed distribution. And what we see in the observed distribution is that if we have a solid dot, it's within the expected distribution. And then if we have an open dot, it's statistically significant occurrence of cold air outbreaks after these events. And so what we see is that after something like a sudden stratospheric warming event, cold air outbreaks are only significantly increased with respect to what's expected in the 1 week after a sudden stratospheric warming event. So these big headlines that say, oh my gosh, polar vortex is attacking us, we don't get the subseasonal impact from stratospheric variability here in the US associated with those sudden stratospheric warming events. Where we do see some increased likelihood of occurrence is associated with these wave reflection events. And it's the wave reflection events as identified by the meridional eddy heat flux metric in weeks 1 and 2, but that easterly shear in the upper stratosphere at weeks 3 and 4. So this is an interesting result, especially because the important variability in the stratosphere doesn't come from the types of variability that have been the focus of research for the last decade or so. So again, this is summarizing. We see that these wave reflection indices are the important ones for variability over the US with respect to cold air outbreaks. And unfortunately, our big news stories don't really capture that. So we need to start thinking about, especially with respect to US extremes, Rossby wave reflection during the wintertime. Okay, so this is just the occurrence of cold air outbreaks, but if we look at the duration and the area, we see that in these red dots here, for the duration of cold air outbreaks associated with the sudden stratospheric warming, we have much shorter cold air outbreaks than we would expect. And then the area is also in the bottom quartile for cold air outbreaks after sudden stratospheric warming events. So this is also not intuitive with respect to what you hear in the media. So it's these other types of stratospheric variability that see the biggest impacts. And so what I want to do as I close out here is this is just thinking about colder outbreaks. But there's, like I said, there's other types of billion-dollar disasters that happen in the wintertime. And, you know, severe storms are the biggest types of variability. And so if we think about this, in 2020, so if you look at this map, you don't really see any big winter events, but there were some huge winter events, billion-dollar disasters that happened. For example, in February 5th through 7th, there was a severe weather outbreak in the southeast associated with a lot of hail reports, 66 confirmed tornadoes, $1.5 billion in losses. So this isn't typically what you think of when you think of winter extremes, but this particular winter extreme was also associated with a Rossby wave reflection event. And it was a beautiful example of a Rossby wave reflection event. So I want to show you what this looks like from this case study perspective. Okay, so what you're looking at here in this animation is the GFS forecast for the structure of the Rossby waves. So where you see red, we have ridges. Where we see blue, it's troughs. And what you're looking at in this animation is the GFS was able to forecast on these shorter time scales the Rossby wave reflection event. And then what you're looking at in this 4 panel is these 2-day averages of the wave activity flux. So, you know, where is that wave energy going? Going from the 2nd and 3rd of February 2020, all the way to the 8th and 9th of February 2020. And what we're looking for here is this upward pulse of wave activity flux coming from Siberia. And this is our Siberian high right here at the surface, this little blip of red. And then we have a deep trough sort of extending towards the date line. A lot of Rossby wave activity flux going into the stratosphere. And then as this reflection event evolves, we see this wave activity flux turning back down towards the troposphere. So this is a really great example of a Rossby wave reflection event. And what I've highlighted here is it starts with the appearance of a Siberian high. We see the amplification of a Gulf of Alaska ridge at the tropopause level. And then we see this really high amplitude Hudson Bay low. And that's a good signal of this really amplifying trough over North America. The other thing I want to mention is this line that you see here is the zonal mean wind at 60 degrees north, which is how we measure the strength of the stratospheric polar vortex. And we had a strong vortex event, an easterly shear in the upper stratosphere, and our eddy heat flux. So we had 3 types of stratospheric variability during this event. Now, the impacts, we already know that there was a $1 billion disaster on the 5th through 9th of February, or 7th through February. But downstream, so this is the one that I highlighted on our map. Downstream of that, on the 8th and 9th of February, as this huge trough worked its way across off the East Coast, we had an amplification of the North Atlantic jet that was associated with a new record from JFK to Heathrow. Flight made it in under 5 hours, which is incredible. The average is 6 hours and 15 minutes. So wave reflection event, really deep trough, strong pressure gradients associated with tropopause level flow. And then over Europe, so this is a satellite of the North Atlantic sector. And we had 2 back-to-back cyclones. Both were named cyclones, European windstorm Sierra and Dennis, that were associated with 1.5 billion in euro losses. So this Rossby wave reflection event was associated with a series of high-impact weather events from North America to Europe. And, you know, again, they had precursors in the stratosphere. So our question is, you know, what was the role of the stratosphere in influencing the tropopause level dynamics that led to the precursors to these extreme events? And also, how did that feed back onto the synoptic dynamics for these individual extreme events. So these are the types of questions that my research group is thinking about. And we've done the analysis of looking at the billion-dollar disasters and the stratospheric precursors to these. And what we saw is that strong vortex events tend to be significant preceding these billion-dollar disasters, again, which are loaded to be these severe convective events. And what really is happening during these strong vortex events is that we have reduced ridging off the west coast during strong vortex conditions that enhances the likelihood that you're going to get a trough over the Rockies that can then be associated with that elevated mixed layer to spin up the convection downstream. So these are all things that we're looking at. We don't have the answers yet, but this is the direction that we're thinking about. So to summarize, again, we're thinking about stratospheric variability and cool season extremes. We know that the stratosphere and its variability can lead to windows of opportunity forecasts. It's part of a larger story when we're thinking about this subseasonal timescale. And what we're really emphasizing is that there's different types of stratospheric variability that we haven't really paid attention to, but are important to North American extremes in particular, especially the stratospheric Rossby wave reflection events. They're linked to cold air outbreaks, but also other types of extremes. So this is really what we're emphasizing in our research. And if you walk away with anything, know that we go beyond just sudden stratospheric warmings and strong vortex events. And there's a lot of dynamics going on that we have to think about in this three-dimensional space. And so with that, I'll wrap it up, and I'll be happy to take any questions.
Thanks, Andrea. That was great. I'm going to go online first since Rabat's been waiting since the middle of the talk with his question.
Oh, yeah.
So I think you might have actually talked about this. I think Rabat might have missed it. So it says, we see from the plot. So he asked us back on the plot where we were showing the February 15th cold air event that we see from the plot that almost all of the S2S models failed to reproduce this event. Were all of these low top models, or some of them were high top? I think you sort of talked a little bit about that.
I think he was like going into my next slide, maybe when, but yeah, so the models here are color coded. The purple ones are the high top models, the yellow ones are the low top models. So there was some variability, but it was especially in this northern week 3 forecast period where we saw the biggest difference. And we've related that to the fact that these high top models got the wave reflection event, and that was the precursor for the trough that really brought the cold air to the northern part of this event. And you can, looking at these thumbnails, you can kind of see that, yes, the cold air gets to the northern sector first, and then it appears that the synoptic variability is really what brought the bulk of that cold air to the southern part of, Texas and Oklahoma. So it was really a 1-2 event.
Thank you, Andrea. From a non-stratospheric person,
yes,
could you clarify what is the difference, if anything, between a stratospheric polar vortex and a sudden stratospheric warming?
Yeah, so a sudden stratospheric warming can happen to the stratospheric polar vortex. So a sudden stratospheric warming is a type of variability where the stratospheric polar vortex, which is really just the circumpolar jet and that cold air, warms rapidly and gets distorted. So it can be distorted and elongated. It can be split in two. It can be displaced off the pole. But really, it's associated with a weakening of the circulation in the stratosphere and a warming of the vortex core.
And do we know why those occur?
So yeah, those definitely occur because we have, and I'll go back to, if I can find it quickly. Right, so here, they occur because we have anomalous wave activity that has a vertical component to the group velocity propagation. So this is really, there's a vertical component to the Rossby wave activity flux that goes from the troposphere to the stratosphere.
So the troposphere is forcing the sudden stratospheric warming.
Yeah, and it doesn't always happen. You can have an accumulation of the wave activity in the stratosphere that eventually leads to wave breaking and,
Thank you.
yeah.
Great talk. I was wondering if these Rossby wave reflections happen in other places around the globe and how impactful they are to, I know your work is funded by NOAA and stuff like that, but yeah, how impactful they are to other places.
Yeah, that is a really good question. And I went to a conference, when was it, last year, and somebody actually did that analysis, but they haven't published their work yet. So I can't say, oh, go look it up in this paper. So it's not out yet. But wave reflection from Siberia to North America is the most common, and that's largely due to the background structure of the planetary waves in the stratosphere. So frequently the source of the wave activity that enters the stratosphere is that Siberia region. So it largely is determined by just the climatological wave structures. You can get it in other locations, but it's less frequent. And how it impacts other locations is a huge open question, and I don't have an answer to that one. Yeah.
So I was wondering, how confident are we of the representation of the upper stratosphere in Era 5?
That is a great question. Fairly confident. There's been a lot of work. There's a stratosphere reanalysis intercomparison project. So they've done a lot of work to really answer that question. And ERA 5 is one of the best data sets there are out there. And a lot of their analysis has compared it to the observations that we have from satellite data. And so it does a pretty good job. We know that there's some inconsistencies, and for a while there were errors and there was a cold bias in ERA 5, but that's since been updated. So there are people working on that, but it's not bad.
Yeah, so you opened up with showing us the S2S models kind of failing miserably with this one event. Do you have like a case where they succeed spectacularly? Like Morris usually shows us cases where they succeed spectacularly.
Yeah, I'm trying to think of one, and I don't have one off the top of my head.
And if not, why not?
Yeah.
And if not, why not?
So, no, that is a good question. And I'm trying, off the top of my head, I don't have a great example. But the variability in lead time for predicting the impacts is different with each case. And there are some models that can do it out to 20 days. And it's actually in this, let's see if I can get there. So this Madison et al. Paper, there is a section there where we do look at the success stories and how some models have more lead time and are better at predicting than others. So this is, of course, the upward side. This paper also gets at the downward side. And so that information, I don't have it off the top of my head, but it is in there. Yeah.
Andrea, the Russian connection is interesting, or Siberia. I can ask it in several ways. What does Putin know that we don't know? Or a non-political question would be, what is the role? Can the Ural Mountains, north-south, play any role in the upward reflection? Why does it start in Siberia?
Largely because it's the planetary wave structure. So if you think about, and I don't know if I have a really good, let me see here. Maybe this composite. So if you just look at this composite of where the polar vortex is during these cold air outbreaks, so the black contours here, this is really a wave 1 structure. And so if you think about, this is all the way at 10 hectopascals, but if we think about where we can get wave 1 into the stratosphere, really what we're doing is we're having a source in this region, and we're amplifying that wave 1 structure sort of to be locked into this phasing. So we have a trough basically over Eurasia and a ridge over the Gulf of Alaska. And that's just the structure. So why is that the case? There is a lot of topography associated with it. And typically we get that Siberian high as that surface precursor to the vertical westward tilt with height structure of Rossby waves as they enter the stratosphere. So I don't think I answered your question as clearly as I wanted to, but it is locked to topography, the high plateau further south, the north-south Ural Mountains, and just the large-scale structure of the hemispheric circulation lead to this phasing of the wave one structure.
You used the word amplification. I was just curious, can you quantify V prime, T prime that's positive versus the V prime, T prime that's negative? Is it actually amplification, or is it just this turning of the flux?
No, we do, and let's see if I can. I don't think this is the best example, but this is a time series for that 1985 event. And I didn't really focus on this, but so the V prime T prime over Canada is in red. The V prime T prime over Siberia is in blue. The difference between the two is in purple. And so you really can't see. In this isn't one of those events, so it's maybe not the best example, but you can see which one is dominating the other. And a lot of times in the events that do make the cutoff, the downward component is exceeding the upward component over Siberia. So we can quantify that. But in general, you can kind of see this gray line in the background. This is the average, the climatological average. So generally, you have more upward over Siberia than you have downward. But there are these events where it's not the case.
And I just want to point out a comment from Andy Heimswald talking about there is some good NASA ER2 aircraft data on, I think we're February 5th, 2020.
Oh, yeah, yeah.
So from the impacts.
From that particular big event.
Yeah.
Yes.
So thanks, Andy, for pointing that out. I think it sounds
Yeah.
like Andrea is familiar with some of that data. So
Yeah, no, that's great. I haven't
all the
looked
data
at
we
it.
can get.
I know.
All right. Well, I know I have more I could ask, but I'm going to think it's good to wrap up here so we can have some more coffee and cookies and talk
Perfect.
and ask more questions. And thanks, everybody. And let's thank Andrea one more time for a great talk.
Thanks, everyone.